Hello friends, welcome to Bindu Dhadwal chemistry lessons. The topic that we take today is polarity of bonds, dipole moment. Sodium chloride is an ionic compound, hydrogen is a covalent compound. The existence of a 100% ionic or covalent compound represents an ideal situation. In reality, no bond or compound is either completely covalent or ionic. These molecules, which are homoatomic, both the atoms are same, the electron pair lies in the middle of the two atoms. In heteroatomic molecule, the covalent bond is nonpolar. The more electronegative atom attracts the shared pair of electrons towards itself, and so the shared pair of electron between the two atoms gets displaced more towards the fluorine atom, since it is more electronegative than hydrogen. As a result, there is a partial negative charge on fluorine atom and partial positive charge on hydrogen atom, that is, two poles have developed. So this kind of a resultant covalent bond is called polar covalent bond. As a result of polarization, the molecule possesses the dipole moment. The dipole moment can be defined as the product of magnitude of the charge and the distance between the center of positive and negative charges. It is represented as mu, and its mathematical formula is charge into distance of separation, Q into R. Dipole moment is usually expressed in d by units with the symbol d. The conversion factor is 1 d by is equal to 3.33564 into 10 raised to power minus 30 coulomb meters. It is a vector quantity, that is, quantity which depends on the magnitude as well as the direction is called a vector quantity. In chemistry, the presence of dipole moment is represented by a crossed arrow. Cross is put on the positive end and arrowhead is put on the negative end. This arrow symbolizes the direction of the shift of electron density in the molecule. In case of polyatomic molecules, the dipole moment not only depends upon the individual dipole moment of bonds, known as bond dipoles, but also on the spatial arrangement of various bonds in the molecule. In such a case, the dipole moment of molecule is the vector sum of dipole moments of various bonds. For example, water is a polyatomic molecule. There are two polar bonds. So the dipole moment of the whole molecule will be the sum of the two vectors. So this vector and this vector, the resultant of addition of these two vectors is in this direction. So water on the whole is polar, having a dipole moment acting in this upward direction. So it has a bent structure. The bond angle is 104.5 degrees. This bond angle decides what will be the resultant of the whole molecule, dipole moment. The net dipole moment will be 6.17 into 10 raised to power minus 30 coulomb meters. In d bys, the dipole moment is 1.85 d by, and when you multiply 1.85 into 1 d by is equal to this much coulomb meters, so multiplying you get this value, 6.17 into 10 raised to power minus 30 coulomb meters. This was for a bent structure. Dipole moment of beryllium fluoride, BeF2. Now BeF2 is linear, so its dipole moment is 0, because though both the bonds are polar, the bonds are pointing in opposite directions. The dipole value in both the bonds is equal, but in opposite direction. So resultant, because the vectors cancel each other, so the resultant is 0. BF3. The shape is trigonal planar. The bond angle between them is 120 degrees. on the whole, when you add all the three dipoles, the bond dipoles, the total net dipole moment comes out to be 0. The resultant of any two is equal and opposite to the third. So the tetraatomic molecule like BF3 is non-polar even though each bond is polar. Now in interesting case in ammonia and NF3, both the molecules have pyramidal shape with a lone pair of electrons on nitrogen atom, and although fluorine is more electronegative than nitrogen, even then this molecule has less dipole moment than ammonia. This is because the orbital has some dipole, and these three bonds have dipole pointing towards nitrogen. Their resultant and the dipole of the orbital, they are pointing in the same direction. But in case of NF3, the dipoles are pointing in this direction, so resultant of these three bond dipoles is in the downward direction, whereas orbital dipole is in upward direction. These two cancel each other, so net dipole reduces. So in case of ammonia, the dipole moment is 1.47 dBi, whereas in NF3 it is reduced to 0.23 dBi. It may be concluded that the presence of polar bonds in a polyatomic molecule does not mean that the molecule as a whole will always have dipole moment. You have seen carbon dioxide dipole moment is 0, BF3 it is 0. In case of methane, the tetrahedral shape also, all the four carbon hydrogen bond, though polar, they are equivalent to each other. Their vectors add in such a way that they cancel each other and the net dipole moment is 0. Same is the case in carbon tetrachloride. But in chloroform, where there is one carbon hydrogen bond and three carbon chlorine bonds, there is some net dipole moment, and as a result the dipole moment is greater than 0. It is polar in nature. Importance of dipole moment. This we can, with the help of dipole moment, we can distinguish between polar and non-polar molecules. So in all these molecules which have 0 dipole, hydrogen, oxygen, chlorine, nitrogen, carbon dioxide, beryllium fluoride, boron trifluoride, methane, they have 0 dipole moment, so they are non-polar. And these molecules, these are polar in nature. Second is degree of polarity. Greater the dipole moment, more is the polarity of the molecule. So hydrogen fluoride having dipole moment 1.78 dBi, more polar than HCl having dipole moment 1.07 dBi. Shapes of molecules can be predicted from the value of their dipole moment. Water has the dipole moment 1.85 dBi, means it will have bent shape. And carbon dioxide has 0 dipole moment, means that its dipole moments are cancelling each other out, and so it is linear in nature. Then next importance, we can find out the ionic character in a molecule. It has been observed that when the electronegativity difference between two atoms is 1.7, then the bond is 50% ionic and 50% covalent. If electronegativity is greater than 1.7, the bond is predominantly ionic. If it is less than 1.7, it is more covalent. For example, cesium fluoride, cesium's dipole electronegativity is 0.7, fluorine is 4. The difference 3.3 is greater than 1.7, so it is more ionic than lithium fluoride. Percentage of ionic character can be calculated from the ratio of observed dipole moment and dipole moment for complete ionic character. For example, for HCl, if we assume 100% ionic character, then charge on hydrogen and chlorine will be 4.8 into 10⁻⁸ electrostatic units. The bond length is found to be 1.275 into 10 raised to power minus 8. So we can calculate dipole moment for 100% ionic character in HCl, which will come out to be 4.8 into 10 raised to power minus 8 into 1.275 into 10 raised to power minus 8. This comes out to be 6.12 into 10 raised to power minus 18 electrostatic unit centimeter, or 6.12 dBi. So this is the maximum dipole moment that it can have, provided the bond is ionic. Now what the dipole moment that is observed is 1.07. So percentage ionic character will be 1.07 divided by the maximum 6.12 into 100. This comes out to be 17.48%. So we can also distinguish between cis and trans isomers. In case of cis isomer, a cis isomer is when across the double bond the two substituents are of the same type, are on the same side. Here Cl and Cl are on the same side of the double bond, H and H are on the same side of the double bond. Whereas in this case, these are opposite to each other. So in cis, the vector, this is a polar bond, so the net dipole moment is the sum of these two vectors, and this comes out to be greater than 0. Whereas in case of trans dichloroethene, the dipole moment of this carbon chlorine bond cancels the dipole moment of this one, because they are equal and opposite to each other. So the net dipole moment comes out to be 0. So you can distinguish between the two isomers. The one which is having value 0 is a trans one, and which has greater than 0 is a cis isomer. Distinguish between ortho, meta and para isomers. So in a benzene ring, if the two substituents are on the opposite side of each other like this, it is a para isomer. If the substituents are present on adjacent carbons, this is an ortho isomer. Whereas if they are on 1 and 3rd position, this is a meta isomer. Value of dipole moment for para isomer is 0, because these two cancel each other. These two add up, so it is having more dipole moment than the meta isomer. So the partial covalent character in an ionic bond. This covalent character results because of a process called polarization. To understand polarization, let us assume that this is a cation and an anion under ideal conditions. So you can see spherical nature of both cation and anion. Now a positively charged cation may distort the electron cloud, this dotted one, of the anion towards itself, particularly if the anion is bigger in size. So the electrons tend to come in between the positive and negative charges and thus acquire a covalent character. This process of distortion of electron cloud from the anion towards the cation is called polarization. The cation is said to polarize and the anion is said to be polarized. If polarization is small, the bond is merely ionic. If it is large, it leads to covalent character. So the following assumptions result. When there is no polarization, the bond is mainly ionic. If there is small polarization, the bond is ionic but with some covalent character. If there is large polarization, that means the covalent character has become predominant. The rules which decide how much polarization will be there are collectively called Fajan's rule. So, tendency of cation to polarize and polarizability of anion are summarized in the following rules known as Fajan's rule. The small size of cation. Smaller the size of cation, greater is the polarizing power. So, lithium being smaller in size is polarizing more than sodium. So lithium chloride will be having covalent character, whereas sodium chloride is ionic in nature. Large size of anion. More the size of anion, more is it polarized. Polarization increases with the increase in size of anion. That is why the ions like iodide, bromide, sulfide and selenide, which are bigger in size, are easily polarizable. Third rule is large charge on cation or anion. Larger the charge on cation, greater is polarizing power. It will polarize more if the charge is more on it. Larger the charge on anion, greater is its tendency to get polarized. More is the charge on anion, more it will be polarized. Electronic configuration of cations. It is seen that cations with 18 electron shell configuration, which is called pseudo inert gas configuration, will cause greater polarization than cations with 8 electron shell configuration. For example, we can compare between copper, which has 18 electrons in its outermost shell, and sodium, which has 8 electrons in its outermost shell. It is seen that copper will polarize more than sodium. These d electrons, they have very less screening effect. That means that they cannot screen the outermost electron from the effect of nucleus. That means effective nuclear charge is more for copper, which is having 18 electrons, and less for sodium. So if effective nuclear charge is more for copper, that means the copper nucleus will hold the electrons more tightly and act as a smaller ion and will polarize more. So thank you.